All right, now that we've talked about logarithmic differentiation, we are actually going to be able to use that to help us understand how to find the derivative of exponential functions. So let's say, for example, we were looking at the derivative of e to the power of x. So let me go ahead and write that. I'm going to rewrite this as an actual equation. We're going to write this as y is equal to e to the power of x. Okay, so we're going to define e to the power of x, this exponential function, and we're just going to write it as an equation. Well, we're now going to apply logarithmic differentiation. So you can watch my previous video if you need a recap on this, but effectively the idea here is that we're going to take the log of both sides, and it could be any logarithm, but since my base is e, it makes the most sense to take the natural log of both sides. And I'm going to take the derivative of all this. I'm going to now find the derivative of all this. So this is what's going to allow me to take the derivative of e to the x. So remembering what we remember, the derivative of the natural log of y, well, this is just going to be y prime over y. And this right here, let me just quickly rewrite this using a log property. I'm going to move this x to the front and write this as x times the natural log of e. And the natural log of e is just simply 1. So all of this just comes out to be just x. So I'm just going to write this as x. Oh, I should say, well, if that is just x, I then have to take the derivative of x, which is just going to be 1. Okay, so if I could just write an intermediary step here, maybe I'll just do that just so we're not too confused. This is the derivative of x, because the natural log of e to the x is just x. And then this is y prime over y is just equal to 1, which we can then say y prime is equal to y. Well, if you take a look at this, there's something pretty neat about this. What did we say y was initially? We said y initially was e to the x. So that means y prime is e to the x. And I think that's super neat, that the derivative of e to the x is e to the x. And this is the first time we've seen a function whose derivative is the function itself. And on a conceptual level, that is sort of crazy. Now, if we were looking at the derivative of something that weren't just e raised to the power of x, because what's easy about this one is that the derivative of x was just equal to 1. What if we were to take a look at something like, let me just write this over here. What if we were to take a look at something like finding the derivative e to the power of some other function u, where u is just some function. We'll just call this f of x. Well, if I take the natural log of both sides and I take the derivative of all this, we can then say this is y prime over y. This again is going to be the derivative of u times the natural log of e. Well, again, the natural log of e is just 1, so we can write this as the derivative of u. And y prime then is going to be u prime times y. And what did we say y was initially? Y was equal to e to the u. So we can just simplify this as u prime times e to the u. So that's what's pretty neat about this first to start off, was we can look at the derivative of e to the x as being just itself. And if we're raising e to some other power, some function u, then the derivative of e to the u would just simply be the derivative of your power times e to the u itself. Okay? All right, well, what about when we're finding the derivative of some base other than e, something like b to the x? Well, I want to kind of point your attention to this fact right over here, that some base raised to the power of x is equivalent to saying e to the power of x ln b. Well, why is that the case? Well, if you just recall, this is equivalent to saying e to the power of natural log of b raised to the x. And there is a logarithmic property that says if we take something with a base e and raise it to the power of a natural log of some argument, then all of this is simply that argument itself. Okay, so what that allows us to do is if we're taking the derivative of b to the x, I can rewrite this as the derivative of e to the natural log of b to the x, or just e x ln b. Okay, so now we're going to differentiate this. So let me just kind of draw our attention here. So now if we differentiate this, what does this give us? Well, we're going to just temporarily let u be equal to x ln b. Okay, that is to say we're going to rewrite this as e to the power of u. And what that does is it allows us to use the rule that we just came up with, right? That the derivative of e to the u is just, is u prime times e to the u. So for us, we just need to come up with the derivative of u. So u prime is just going to be the natural log of b, right? Because the natural log of b is just some constant. So if that is the case, using this rule up here, we can say the derivative of e to the u, this is just going to be equal to u prime times e to the u. U prime is the natural log of b, and we're saying e raised to the x ln b power. And initially we said all of this is just simply equal to b to the x. So this simplifies out nicely to the natural log of b times b to the x. And that's our rule here that we can summarize. So to find the derivative of some exponential function with some base other than e raised to the x power, it is simply the natural log of that base times the function itself. And of course, there's a chain rule version of this, where if we're raising our base to some function, which we can call u, then we just need to remember to multiply by u prime there as well. Okay, so let's try a couple of practice problems with this. Okay, let's take a look at numbers 1 and 2 here, where we're going to find the derivative of these functions. Well, the first one is base e, so this would be us leveraging this rule here. So if we say u is equal to 2x squared minus 1, u prime is equal to 4x. So y prime then here would be 4x, or u prime, this is our u prime, times our original function itself, e to the 2x squared minus 1. This is our e to the u. Okay? All right, well, what about something like number 2 here? Well, this time we're going to be using the product rule, right? So we're going to say y prime is equal to the derivative of x, which is 1, times e to the 2x, plus x times the derivative of e to the 2x. Well, e to the 2x, again, we're using this rule here, is going to be 2 is the derivative, or that's our u prime, times 2 times e to the 2x. So this is going to clean up nicely to e to the 2x plus 2x e to the 2x, which you don't have to do, but it might be a good idea to just make sure we know how to simplify this if we need to, because if we were asked to do something like the first derivative test, or maybe use the second derivative, or it'd be nice to have the simplified form of this. All right, let's try a couple other ones. What about something like number 3? Well, this is our first example of a problem where our base is not e. So we're going to say f prime of x is equal to the natural log of our base, so the natural log of 3, times 3 to the natural log of x, times the derivative of the natural log of x, right? This is, again, actually us applying this rule, times the derivative of the natural log of x, which is 1 over x. So if I should kind of make sure that we understand each part that we just found, this is our u prime, this is our b to the u, and this was our natural log of b. Okay, and then finally, g of x here, we're just going to apply, again, the product rule. So we're going to say g prime of x. This would be the natural log of 3 times 3 to the x times 4 to the x. So that's our product rule. This is our this is our f, and this is our g. This is our f prime, and this is our g. All of that plus f times g prime. So 3 to the x, this is our f, times g prime, which is the natural log of 4 times 4 to the x. This is our g prime. And we can leave it written like that, or we could just clean this up and simplify this as 3 to the x, 4 to the x, the natural log of 3 plus the natural log of 4. Okay? All right. Go ahead and pause the video right now and work through numbers 5 through 7. Well, for 5 through 7, if you've had a chance to work through it, we can say f prime of x would be equal to, if I apply the product rule here, e to the negative 2x squared plus x times negative 4x times e to the negative 2x squared, which I can then simplify. Let me just zoom in here. I can simplify to e to the negative 2x squared times 1 minus 4x squared. Okay? If I then am using the first derivative test, I'm going to set this equal to 0. And I can set e to the negative 2x squared equal to 0, which I could rewrite this. Let me actually do this somewhere else, just so I have enough space. Let me do this over here. If I set 0 is equal to e to the negative 2x squared, this is equivalent to saying the natural log of 0, which is equal to negative 2x squared. And this is undefined. There's nothing else that we can really do here. So we don't really have to worry about this providing any zeros. What about setting 1 minus 4x squared? Let me do this. 1 minus 4x squared equal to 0. Well, this just cleans up to x is equal to plus or minus 1/2. So let me go ahead and move this, make this a little smaller so we have some space to work with. So drawing my f prime number line, I've got negative 1/2, positive 1/2, negative, positive, negative, negative, positive, negative. That means my relative minimum is going to occur at negative 1/2. And when I plug that into my original function, I should get negative 1/2 e to the negative 1/2. And my relative maximum is positive 1/2, 1/2 e to the negative 1/2. Okay, so there's my relative maximum. And I don't have to worry about finding any absolute extrema. The problem only asks for relative extrema. Okay, now what about any inflection points? Well, here I'm just going to take my second derivative, or find my second derivative. So I got to differentiate all of this. And maybe we want to treat this as our f and this as our g. Well, all of that's going to come out to negative 4x times e to the negative 2x squared times 1 minus 4x squared. That's my f prime times g. And then this is my f times g prime, which I can then clean up a little bit as such. And again, setting each of these equal to 0, I know that when I set this equal to 0, I don't have to worry about any solutions from that. If I set this equal to 0, this is going to come out to 0 is equal to negative 4x times 3 minus 4x squared, which means x is equal to 0 and plus or minus root 3 over 2. So that is the case. If I draw my f double prime number line, I can put those possible inflection points here on my number line. When you plug in these values from each of these intervals into your second derivative, you should get negative, positive, negative, positive. So concave down, up, which means my actual inflection points, and this is where we would need a calculator unless you want to do all this by hand. These are our actual inflection points. 0, 0 is the second, and we have another one here. Okay? And then question number 7 was asking, what about the end behavior of this function? Well, if I just rewrite this function in this form, this might be a little bit easier to see here. Well, we notice that this denominator is growing way more quickly than the numerator. The numerator is growing at a linear rate, whereas my denominator is growing exponentially. So we could say that the limit of this function, as x approaches positive and negative infinity, is just going to be equal to 0 because the denominator is growing way more quickly than the numerator. And if you were to see the graph of this function, it should look something like, assuming that I actually can graph properly, but something like that. But as x approaches positive and negative infinity, f of x should approach 0. Okay? Now, the final part of this lesson is to actually talk about integrating exponential functions. And again, you could sit here and you could just memorize these rules, but I want to make sure that we understand the why behind all of these. If the derivative of e to the x is the function itself, then it makes sense that the integral of e to the x is simply e to the x plus c. Now, what if we were integrating, however, something that wasn't just, where the power wasn't just x? Let's do something like negative 5x. Well, the idea here is essentially just the same thing that we've done so far with integrating, with us making sure that we know how to reverse the chain, or if you want to call it u substitution, do that. If, for example, we said let u be equal to negative 5x, that means du has to be equal to negative 5 dx. That is to say, in order for me to integrate this, the derivative of negative 5x has to be in my integrand. So I can say e to the u, or let me actually just leave it as negative 5x. But I have to have negative 5 dx in my integrand. And so I can easily multiply by negative 5. I just need to make sure that I also have negative 1/5 out here. And I should probably put this in parentheses. I need to make sure that I have a negative 1/5 so that I'm not changing the value of my integrand. Well, if that's the case, now I can just say negative 1/5 times e to the negative 5x, because the integral of e to the u is just e to the u. As long as I have the derivative of u in my integrand, all of that plus c. Okay? And again, then, so that kind of formalizes these two rules that we have there. And again, what about when our base is something other than e? Well, again, I'm going to leverage this fact here. So what I'm going to do, let me actually just make this smaller. Some space to work with. So again, I'm going to rewrite this as e to the power of x ln b. And just like we did before, we're going to treat this as our u, where we would say, let me do a different color, u prime is just simply equal to the natural log of b. Okay, so if u prime is the natural log of b, we can think of this as, we can integrate this as e to the u. We can rewrite it as this form with our base is e. So we can write this as e to the u as long as we have u prime in our integrand. Well, in order to have u prime in our integrand, we could then just move this over here and write this as the natural log of b, as long as we have 1 over the natural log of b here on the outside. Okay, so now we see this as our du, or u prime. There's our u prime there. I probably should have written dx here. There you go. There's our dx. So now we can just rewrite this as, this would just be 1 over the natural log of b times b to the x plus c. Okay? And again here, all I did at the very end is I replaced e to the x ln of b, e to the x ln of b back with the b to the x. Okay? And again, there's a reverse chain rule version of this as well. So let's go ahead and just practice integrating a few of these integrals. So for something like number 8 here, well, I'm going to think of this as, here is my u, and you don't have to define these. This is x squared minus 1. That means du would be equal to 2x dx. So that is to say, I can rewrite it as such. This is 0 to 1/2, 4 raised to the x squared minus 1. In order for me to just integrate this, just so I can apply this rule over here, I've just got to make sure that I have a 2x dx. Well, I have an x, I have a dx already, I'm just missing a 2, which I can then easily multiply by 2 and then multiply by 1/2. And now now I can actually apply the formula. 1 over the natural log of our base 4, okay, times the 1/2 that we wrote so that we can integrate. Now I can unhook this chain, if you will, and then this would be our original function b to the x, so 4 to the x squared minus 1, all of this evaluated from 0 to 1. Okay, and let me just make this a little smaller so we can evaluate this. And this should come out to 4 to the negative 3/4 power over 2 natural log of 4 minus 4 to the negative 1 over 2 natural log of 4. Okay, there's our answer there. All right, for number 9, we can rewrite this, if it helps at all, as e to the 2 over x times 1 over 3 x to the negative 2 power dx. So I'm going to move that 1/3 over to the outside now. And then move this a little bit. Oops, move all of this here. Okay. So if we think of this as our u, which is 2 times x to the negative 1, we can say that du would have to be negative 2 over x squared, or negative 2 times x to the negative 2 power. So we already have, well, we can actually even just write this. We already have an x to the negative 2. And we have a dx. All we're missing then is that negative 2. So again, we could just multiply all of this by negative 2. So let me write this here. We already have that 1/3. We're going to multiply by that 1/2. E to the 2 over x times 2x to the negative 2 dx. And this comes out to, oh, I apologize. We needed a negative 2, didn't we? Negative 2, which make this negative 2. All right, so now we can say negative 1/6 e to the 2 over x, all of that plus c. And I realized I never closed my parentheses here. Okay. All right. Last but certainly not least, let's try number 10 here. So for number 10, we're going to write this. I apologize, there was a typo here. I'm going to move that 4 to the power of the denominator, in case you haven't already fixed that. So we're going to say let u be equal to e to the x plus e to the negative x. That means du is going to be e to the x minus e to the negative x. And well, what do you know? All of this here appears to be our du. All of this here can just be thought of as our u. So we can actually rewrite this as u to the negative 4th du, right? Or we can just think of this as e to the x plus e to the negative x, all of that to the negative 4th, times du dx however you want to think about it. But if you think of it this way, then this is just going to be e to the negative 3rd over negative 3 plus c, which comes out to e to the x plus e to the negative x, all of that to the negative 3 power over negative 3 plus c. And I need some space to write my constant of integration. Okay? All right, so hopefully this helps understand how to find both the derivatives and the integrals of exponential functions.